Okay, so in the last class we were uh, looking at the um, effect of the nuclear magnetic moment on the uh, electronic levels, and one of the matrix element that we wanted to we encountered was a matrix element which involved operator gk, which was uh, the orbital angular momentum minus the spin angular momentum times an additional piece, which was depending upon the radial vector. Okay. And what we did was we kind of used Vignerica theorem in multiple ways to simplify the expression. And basic point of Vignerica theorem is that if you are using a spherical tensor of a specific kind, then you can the matrix element of that spherical tensor is same as the matrix element of any other spherical tensor if it has the same rank. Okay, and therefore only thing that you need to determine is the proportionality constant between two such spherical tensors, and that those proportionality constants are independent of the magnetic projections of the states. Okay, so that is the main result of the Vignerica theorem. Of course, what is called the reduced matrix element in the Vignerica theorem is something that you need to compute explicitly. And what we did in the last class was we kind of replaced these operators by a suitable set of spherical vectors, namely jk, in fact, in this particular case. And then since these states are summed over alpha, which is like essentially identity element, you kind of get rid of that and you get a jk times jk, which is the j squared operator, and you compute the eigenvalues of j squared, which are just j into j plus 1. That is a kind of trick that we used to determine this matrix element mgj. The reason for determining that we got into determining mgj was the one which would tell us how to determine this proportionality constant k. And what we showed was that the proportionality constant can actually be written after a series of manipulations as an expression which looks like this. Okay, and this expression in fact vanishes for L equals 0 and has a non-vanishing contribution for L not equal to 0. And after you do this computation of the radial matrix element using the radial part of the wave function, the final answer turns out to be something like this. Okay, that k is equal to z squared m cube upon n cube times j into j plus 1 upon L plus half. Now this is a contribution that you get from 1 over r cube term in the perturbation perturbed Hamiltonian, or rather the perturbation term in the Hamiltonian. But besides that, there is another term which is the delta function piece. Okay, and that is the term that we will look at today. Okay, so of course you can put this k back into the energy functional to write down this expression, and so this is how this entire expression is going to look like. Okay, fine. So delta function of course contributes only for L equals 0, whereas this expression does not contribute at L equals 0. So they seem to be working on orthogonal subspaces. Okay, now delta function expression involved I dot S, but since L is equal to 0, we can replace that by I dot J and write down this expression again as f squared minus I squared minus j squared. Okay, and that will give you eigenvalues, which is half of f into f plus 1 minus I into I plus 1 minus j into j plus 1, which is precisely the kind of expression that you get here. This and this factor of 2 sitting in the denominator. Okay, then you can notice that there is a e by m also sitting around, so that also you get it right. Okay, what we need to determine is what is the remaining piece that you would get. Okay, that requires, of course, determining the matrix element of delta cube term. Okay, fine. So that is the computation that one has to do by plugging delta function into this integral. The denominator is just ensuring that the wave functions are normalized, and the delta function tells you that all that really matters on the numerator is what is the value of R and L at R equals 0. That is what this delta function will enforce. And we know that R and L is at R equals 0 is 0 if L is not equal to 0. So therefore, we don't really care because that is the case in which this contribution would just be 0. Non-zero contribution comes when L is equal to 0, and that just tells you what is the amplitude of the S wave radial wave function at R equals 0, divided by, of course, its normalization factor. That turns out to be a quantity like this. And as I was telling you last time about 1 over R cube, here also delta function dimension counting tells you that you would naturally get Z E squared M to the 3/2 factor, sorry, to the third factor simply because of dimension counting, because it is just inverse Bohr radius. Okay, fine. So you take this factor and plug it back in, and you get the answer. Remember, just take a look at this piece. You have 8 pi by 3 E by M GL mu N times this entire sector. Okay, so you get all that stuff sitting around here. 8 pi by 3 GL mu N, this half coming from this factor. F squared minus I squared minus J squared gives you this term. This integral gives you Z cube e to the 6 M cube upon pi N cube. Okay, and there is an E by M factor. Okay, so entire stuff is written out here. Okay, and now what we need to do is compare. Okay, so since you want to compare, okay, okay, so here is the result. Okay, so this is the result for 1 over R cube term, and this is the result for the delta function. Okay, now so let me scroll it a bit up just to kind of make it a point, or maybe that's not going to help. Probably, yeah, maybe it will. Okay, so this is a term. Okay, now notice one thing, that all the terms sitting around here, that Z squared M cube upon N cube, this pi is going to cancel with this pi, so you don't worry about pi factor. Mu L G N by sorry, excuse me. Yeah, mu N G L by 2 factor, which is sitting around here. E by M is also a factor sitting around. This entire bracket is also sitting around. Okay, so what matters here is really 8 by 3 factor versus this entire J into J plus 1 into L plus 2, L plus half. But you notice one thing, that when you are working at L is equal to 0, then this is really half. Okay, and when L is equal to 0, J is just half, and therefore that is 3/4. So 3/4 times half gives you 3/8. Put 8 in the numerator and you get precisely that factor. Okay, so therefore, even if these two computations are independent, okay, eventually you can write down the entire expression like this. Okay, and all you have to do is to lift the restriction that L is not equal to 0 in this particular computation, because L is not equal to 0 for 1 over R cube, but L is precisely equal to 0 for the delta function, and these two expressions are identical. Okay, so therefore what we will do is we'll just merge those quantities and write down the entire expression like this. Okay, so notice one thing, that I have written down Z. There's a e to the 6th term here and a e term here, so it should have been e to the 7. But then nuclear magnetic moment can also be written as e upon 2 times the proton mass. So therefore, if you write it in terms of that, then you get a z cube e to the 8 is sitting around there. Okay. The reason for writing the nuclear magnetic moment explicitly in this particular form is just to emphasize the point that these corrections are very small. First of all, the numerator mass term is the electron mass term. Denominator is the proton mass term. This number could be larger, in fact, if you are looking at heavy nuclei, but it doesn't really matter. We need not worry about that factors. Okay, I mean that may shave off 1 power of z out here. Okay, but what is important here is that the mass of the electron is about 1836 times smaller than the proton mass. Okay, or to put it a little differently, you can write down proton mass in the electron mass form, which is 1836 times the electron mass. Okay, but there's an electron mass squared piece, so therefore this factor is much smaller than the kind of factor that you would have expected by doing the original exactly solvable Schrodinger equation problem, in which the energy splittings are much larger and never suppressed by the nuclear masses. Okay, fine. So it is understandable that these corrections are small because of the nuclear mass, but we could ask a question that with respect to the original problem, but we could ask a question, how do they compare with the relativistic correction? Remember, there was this p to the 4 type of correction that we had in our relativistic problem, and we said that, like, okay, that is a relativistic correction, and then there are some nuclear magnetic effects, and we just concentrate on nuclear magnetic effects. Now, one can of course compute the relativistic corrections, and the relativistic correction is something we had looked at, which is what we call fine structure splitting, and that quantity is this. Okay, and this quantity is again contains z to the 4 e to the 8 upon times m upon n to the 4 kind of factor, and and so that is multiplied by this thing. And if you want to recall, Schrodinger decided not to get into this relativistic formulation because he did not get this j plus half factor. That was the thing. That was the problem he had when he tried to solve the what is called the Klein-Gordon equation. Okay, so now what we want to do is to compare this expression with the expression that we get here. Okay, so maybe I just kind of scroll it down. I mean, it's the same kind of expression. So, okay. So these are some order 1 numbers sitting around here. Okay, what is important is really this factor sitting to at the extreme left. And here you have a factor m sitting around here, and here you have a factor which is m squared upon proton mass sitting around. So therefore, this splitting versus this splitting has 3 orders of magnitude difference. Why? Because m upon m proton is roughly 1 upon 2000, 1 upon 1836 to be very precise. Okay, so that is like 10 to the 3 factor in the denominator. Okay, so therefore, the fine structure splitting is definitely much larger compared to this nuclear magnetic effect, which are much smaller splittings. Okay, and clearly, as I said, that it's a proton mass sitting in the denominator, which is affecting the splitting magnitude of the splitting, and because this magnitude is small, we call the splitting generated by nuclear effect hyperfine splitting. Okay.
So,
yes.
Shouldn't we keep like we were talking about the magnetic moment of the whole nucleus?
Yes.
So why is there only one proton in the magnetic moment when you are calculating magnetic moment?
Yeah. So that's what I was saying. That you don't have to write that as a single proton mass. You may want to write that as, say, z protons. Okay.
Okay. Yeah.
So if you do that, it may shave off 1 power of z at best from here. But
yeah.
if you put z protons in the denominator, then the splitting gets even smaller, right?
Yeah.
So this is the largest possible splitting. That's the reason why proton mass is kept here.
Okay, yeah.
Any other splitting will be even finer. Okay, and if you try to make comparison of this with the fine structure splitting, then this is clearly smaller. Okay, and that is the reason why it's called hyperfine. So yes, you could probably put the additional factor here. It will make the splitting even smaller actually. Any other question?
We're still taking this to be some significant number, right?
Yes, yes, because you do observe these kind of splitting experimentally. Okay. In fact, sorry.
In the above thing comes from some it's called Sommerfield expansion, right? Even though we actually
The first one, right?
Yeah.
Yes.
So I mean, there are more terms in the series, right? So which even when we approximate some alpha as a small parameter sort of a thing.
Yes.
So
yeah, but those terms. Yeah, please.
Yeah, if we compare this delta E that we have got here with the next term.
Yes.
Then can we get some order of, because we have been ignoring other terms, right, in the above series.
That is right. So that is the term which is like p to the 6th order term, which is significantly down compared to this. Okay. Yeah, one could do that calculation, but those corrections, the next order correction in the Sommerfield expansion is smaller than these corrections. Okay.
All right.
Yeah. So that is why, that is why one looks at these and not those actually. But otherwise, there's an infinite series sitting around. Yeah. And as I was saying that, like, NMR, the nuclear magnetic resonance, is basically related to these things. NMR is, of course, quite often used in medical imaging and stuff like that. So you do actually use these kind of splitting of states to collect data, do imaging, for example. Okay. Fine. So let's kind of try to figure out what is happening to the setup. Now, remember that all the eigenvalues are written in terms of f into f plus 1, I into I plus 1, j into j plus 1, and nowhere you would see the magnetic projection of any of these angular momenta. Okay. And of course, we are going to work in a basis in which fmf is diagonal. So only quantum number that really matters is mf. And what we find is that, like, all these corrections would lift degeneracies in L, J, S, and so on. But the magnetic quantum number of the total angular momentum is not lifted. Okay. And that fact is related to the spherical symmetry of the problem. Okay. That because of the spherical symmetry, the magnetic projection is not distinguishable. So it continues to be a degeneracy of the problem. Okay. Of course, we just computed magnetic dipole contribution. You could ask a question, what about higher multipoles? Okay. Now, you can eminently compute those also, and they would depend on the size of the nucleus. Remember, if you are looking at the dipolar contribution, suppose you look at electric dipole, then electric dipole corresponds to two charged particles, oppositely charged particles, and distance between them. Okay, that is the dipole, right? So it requires it contains some information about the scale of the object. Okay, so similarly, if you start looking at higher multipole expansion, it would actually take the size of the nucleus into account. But what happens is that, like, when you do, say, dipolar contribution, the dipolar factor is sitting in the numerator. If you remember, if you do multiple expansion for electric field, then you have monopole term, which goes as 1 over r. If you are looking at potential, the dipolar term goes as, suppose you call the dipole to be, say, p, then it goes as p upon r square. It goes up as p upon r square because p contains the charge times the distance between the two oppositely charged objects. So dimensionally, it is same as 1 over r, but one dimension is the size in the numerator is the size of the dipole, and the denominator is the distance of a test particle from the dipole, okay, which is typically very large. Okay, so if you try to do the same thing for multipole expansion, then what you will find is that the nuclear size would appear in the numerator. Okay, like for example, if you do quadrupolar thing, then you get a nuclear size appearing in the numerator, and to compensate for that, higher power of distance between the nucleus and electron will be appearing in the denominator. Now, that distance is already about 5 orders of magnitude larger than the nuclear size. Okay, nucleus is roughly 10 to the minus 15 meters, whereas atomic size is of the order of 10 to the minus 10 meters. So it's like 5 orders of magnitude difference. So therefore, if you start looking at higher multiple moments, they are going to be highly suppressed. Okay, in fact, the suppression factors are going to be something like this. That these suppression factors are, of course, suppression factors with respect to the non-trivial hyperfine contribution. Okay, there are additional Bohr radius power sitting in the denominator, like 1 over r cubed. So it should, I should have really written down rb to the k plus 3 really. But we are just doing a comparative study, so this suffices actually. Okay, so what you have is the size of the nucleus upon the Bohr radius whole to the k. You are essentially computing the expectation value of this. Okay, if you are looking at k's multiple, okay, or rather k plus 1 is multiple really. Okay, now because the Bohr radius is sitting in the denominator, you get z squared m to the k in the numerator. That they are same quantities. Okay, on the other hand, rk, the nuclear size is roughly related to the proton mass, inversely proportional to the nuclear mass really. Okay, and therefore roughly this quantity would look like z squared up m upon the proton mass. Okay, and that's why these factors are now going as m upon mp to the k. So initially for k is equal to 1, which was the dipolar contribution, we were getting or 10 to the minus 3 suppression. But now if you do a higher multiple, then you get 10 to the minus 3 times k. 3k kind of suppression is going to go much higher. Okay. Fine. So this is the reason why we can justify our multiple expansion. Remember, we initially said that like we will have to do multiple expansions, and we did not give justification as to why we need to do multiple expansion, and why is it that we don't take the full distribution at one go and compute. And the reason is that like if you do multiple expansion, you can see the systematic higher multiples are going to be significantly smaller compared to the lower multiples, and therefore within perturbation theory, it makes a lot of sense to do multiple expansion. Okay. Now, of course, so far we looked at only the magnetic moment effect. We could also ask what happens to electric moments. Okay, and of course, we should take electric moments into account. So clearly, nucleus is not a point-like object, and it should in fact be treated as a charge distribution. And if you want to treat that as a charge distribution, it will also have electric multiple moments. Okay, so what we need to do is to look at the multiple expansion of the electric charge distribution. Okay, so suppose we have, I can close this now. Okay, so suppose we have a charge distribution rho. Okay, then the electric potential generated by this charge distribution would be written like this. Okay, so this is supposed to be r prime vector. It's always kind of okay. So what we want to do is to kind of substitute multiple expansion here and look at the terms that the electric potential would give. The monopole term we have already taken care of because that is the part of our exact problem. The other terms are the ones which we want to look at. Okay. We initially said that we are not going to do multiple expansion of this simply because the electron is reasonably far away and it initially sees only the monopole contribution, and that's why we keep the monopole contribution. Okay. Now, we will try to justify why we said that by showing that the dipolar contribution, which is the first contribution beyond multiple contribution, the electric dipolar contribution would vanish. Okay, so the first non-trivial contribution coming from the charge distribution would be at the electric quadrupole level. Okay, so let's try to see that. Okay, so we are considering R to be very large, okay, compared to the size of the nucleus. Okay, and then we are going to expand expand the denominator in terms of by pulling 1 over R out and expanding that in the numerator. Okay, R prime by R factors. So you get terms which are like this. You get 1 over R, which is the monopole term, which we have already used. Then you get R dot R prime upon R cube, which is the dipolar piece. And then you get a quadrupolar piece, which looks like that. Okay, so which is what I kind of expanded, explicitly wrote down pieces. Hello.
Yeah, sir.
Yeah, sorry. Some phone for nothing actually. Okay. So coming back to this, so in this multiple expansion, the first piece, of course, we have already taken care of. This is a dipolar piece. Okay. And then this piece is a quadrupolar piece. Okay. So, so let's look at the quadrupolar piece first, then we'll come back to the dipolar expression. Okay. So this term in the square bracket, okay, so you get the quadrupole moment, which is written like this. Okay, so I just explicitly written it out here. So we'll call it Qij, and it is 3 by 2 times this expression. Okay, now notice that this term is actually traceless. That means if you take Qii, then you get that expression. This term would cancel with this piece, and therefore there is no trace of this Qij. Okay, fine. So because Qij is traceless, and remember we are going to kind of replace this entire square bracket by just Qij. Okay, and since Qij is traceless, this Ri times Rj piece also we can write as Ri Rj minus 1/3 R squared times delta Ij. Okay, so that is the replacement that we will do. Okay, simply because the trace part of Rij would be multiplied by trace part of Qij, but that is 0. Okay, so you can safely kind of do this change. Okay, fine. So so what we want to do is basically compute these quantities in the nuclear ground state, because that is the only state that is going to be really relevant for us. Okay, so the first term is of course the one which is going to give us the total nuclear charge, and that is a piece we have taken care of. The next term is a dipolar piece. Okay, which is this term. Okay, or if you want to look at it upstairs, then it is that term. Okay, so let's look at that piece. Okay, so to compute that piece, what we need to first understand is what is the symmetry of the nuclear problem. Okay, and nuclear problem has like the electromagnetic interaction, the strong interaction also preserves parity symmetry, and therefore nuclear Hamiltonian should preserve parity, okay, because it involves only these two interactions, okay. And if it preserves the parity, then nuclear eigenstates should therefore be parity eigenstates. Okay, so what we will do is that if P is the parity operator, then nuclear eigenstates written in this particular form, IMI, okay, the parity operator acting on that would give you an eigenvalue. That eigenvalue, of course, has to be plus or minus 1 simply because parity operator squares to 1. Okay, so therefore, either the state is parity even or the state is parity odd. Okay, that is the kind of stuff. Of course, you can, you can write down linear combinations of the states with different parities and write down parity non-invariant states. But because the Hamiltonian preserves parity, states with different parities do not mix. They do not have the same energy spectrum also. So therefore, it makes a lot of sense to work in the eigenbasis of simultaneous eigenbasis of Hamiltonian parity. Okay. On the other hand, the dipole, by virtue of having r vectors are in this particular case r prime vector sitting inside it, is odd under parity transformation. Okay, so therefore p times d vector p is actually minus d vector. Okay, so therefore if you compute this matrix element is same as minus times this matrix element. Okay, and now you remember that the parity of the angular momentum problem is related to the angular value of the angular momentum itself, right? Remember that in the spherical harmonics, YLM under parity transformation went to -1 to the L times YLM. Okay, so in this particular case, the parity of these states are determined by only I quantum number and not MI. Okay, so therefore, when you write down the matrix element of D to be minus the matrix element of PDP, then you can choose to act P on the states now, because when PDP acts, when P acts on D, we know that it will just flip sign. Okay, so if you act it on the states, then you get the answer that P acting on I would give you epsilon, and P acting on this I would also give you epsilon. Okay, that epsilon could be plus or minus 1, but since both the states have same I, it will give you the same epsilon. Okay, but it doesn't matter what that epsilon is, because epsilon squares to 1. Okay, and therefore it will give you the matrix element of this to be minus of itself, and only answer to this is that the that dipolar matrix element just vanishes. Okay, so therefore the electric dipolar contribution from the charge distribution of the nucleus is 0. Okay, so the first non-trivial contribution would be quadrupolar, and therefore it, to at least to first order in your computation, you could happily say that, like, I would work with the Coulomb potential and not worry about the multiple expansion of it. Okay, now of course what we will do is we will actually look at the quadrupolar contribution also, okay, and try to find out what it would look like. Okay, but at least electric dipole contribution would vanish. Okay, fine. So now we could ask a question: why is it that we looked at the magnetic dipole moment contribution and when electric dipole moment seemed to have vanished? Okay, and the answer is that the magnetic dipole moment is actually not parity odd; it's in fact parity even. So the magnetic multipole expansion have parity properties staggered with respect to electric multipole expansion. In other words, at quadrupolar level, the electric multipole is parity even and the magnetic quadrupole is parity odd. Okay, so at quadrupolar level, when we want to compute, we would only compute electric quadrupole contribution. Okay, so therefore, if you look at, say, atomic physics book, they will say that let us compute magnetic dipole and electric quadrupole moment contribution without explaining why they are not doing magnetic quadrupole, for example. Okay, but it turns out that the parities are kind of staggered in the electric and magnetic sector. Okay, so any questions about this?
So staggering means?
By staggering means that that if you look at dipolar level, then if I mean, I shouldn't say not, I shouldn't say if, but if you look at any particular multipole, okay, then if the multipole level, if the electric multipole is parity even, then magnetic multipole is parity odd. Okay, if you go to the next one, then the roles are switched. Okay, so for example, at dipole level, electric is parity odd, magnetic is parity even. At quadrupole level, electric is parity even and magnetic is parity odd. Okay, if you go to the next order, you find that electric is parity odd, magnetic is parity even again. Okay, so staggered in that sense that they are
So we'll get
shifted in.
non-zero contribution and zero contribution at each level from each movement.
Yeah, at each level, either only magnetic contributes or only electric contributes. Okay, but not both.
Okay. Okay.
So in that sense, like life is little simpler than what it could have been.
Does nucleus also have a current density?
Yes, of course. Why is that a problem?
I was just wondering, I mean, I thought like if it's a uniform distribution, not uniform, but like spherically symmetric Hamiltonian and all, but can it still have a current density?
Yeah, current density is related to the velocity of the object, right? I mean, charge density times velocity in some sense, right? So in the atomic physics problem, nucleus is not moving, yes, but in general, nuclei are moving, right?
Okay.
So if you are trying to ask what is the current density of a nucleus, it makes complete sense. Like just to look at, I mean, imagine you are doing what is called a heavy ion collision problem. You know, that you are kind of scattering the lead nucleus. I mean, you are accelerating two lead nuclei. Okay, their kind of nuclear charge is some 82 or something. Okay, and you collide them. Okay, I mean, of course, if you are colliding them at like TeV energy, then all the electrons are stripped off because at that energy, atomic physics problem is totally out of the game. Okay, and then you are basically just colliding nuclei with charge plus 82 on a charge plus 82. Okay, and the mass is something of the order of 200 or something. Okay, so you have to define a current for that object, right? That's okay. Is that fine?
Yeah.
Yeah. Okay. Okay. So let's kind of look at the electric quadrupolar case. Okay, we are not going to work this out, but at least we'll try to understand as to how we would go about doing this computation. Okay. Now, if you, yeah, I don't want to roll back like 30-40 pages on in this file, but if you recall that we had said that like if you consider the product of two spherical vectors, okay, then you can decompose the product of two spherical vectors into a scalar quantity, which is the dot product of those two vectors, and then there was a quantity which was written as Wk, which was maybe let's call it Wi, which was epsilon I j k times two spherical vectors, say Vj, Vk, and then there was a symmetric combination which was written as Vj, Vk plus Vk, Vj by 2 minus some 1/3 V square kind of stuff, if you recall that expression. Okay, then this expression is precisely that kind of form. Okay, that you have spherical second rank tensor, okay, generated out of products of two spherical vectors. Okay, so what we are going to do here is that we are going to write down this quantity, okay, in terms of the nuclear angular momentum. Remember, we had done this for the magnetic moment of the nucleus, dipole moment for the nucleus. We said that Mn can be written as GL times mu n times I. Okay, where all angular dependence of that was completely picked up by the nuclear angular momentum I, and its normalization, its kind of overall constant was written as GL times mu n. Okay, we will do the same thing with the Qij fellow. Qij in fact is irreducible tensor, and it is a symmetric combination of the spherical vector. Okay, so we will write this as some constant times half, as I said, there is a factor of half Ij plus Ij Ii minus 1/3 I squared times delta Ij. Okay, I mean, it's pretty similar to the term written out here. I mean, in fact, this term was written in this particular form by using the fact that Qij was traceless. Okay, so this is what is called the traceless symmetric tensor. If you recall, we had discussed this quantity. Okay, we said scalar, vector, and a traceless symmetric tensor. Traceless symmetric tensor, as we had done at that time, has 5 components. Okay, I mean, because Ij takes like 3 values. You look at the symmetric combination, it would have given you 6 quantities, but then you remove the trace out of it, and that's why it has 5. And a spin 2 object in the SU2 or in the angular momentum representation theory also has 5 components. Okay, so you can think of Qij as a spin 2 representation in terms of the angular momentum algebra. Okay, which of course we will write in terms of the spherical vectors in this particular form. Okay, so once you write it in this form, then all you have to do is to basically compute this quantity. Okay, in the by sandwiching it in the nuclear ground state. Okay, that is how the nuclear quadrupole moment would be computed. Now, of course, since it carries information about the nuclear quadrupole, it must be related to E upon MP squared factor. Okay, and you can pull that factor out and write down some other constant. Okay, so but its angular dependence is determined once and for all. Okay, fine. So as I said, that we would kind of compute this quantity by taking its expectation value in the nuclear ground state. Okay, but we will not do it right now. Okay, what we will do now is something little different in the sense that whenever you want to compute quantities of this type, which as you can easily guess are finer than even the hyperfine splitting, because hyperfine splitting has a factor proton mass sitting in the denominator. This quantity has a proton mass squared sitting in the denominator, so therefore it is further suppressed. When you do computations of these kind, you need to ask a question that when you are computing splitting in the electronic level, should you be actually doing degenerate perturbation theory, or should you actually be working with say non-degenerate perturbation theory? Okay, and to understand that, we can kind of we can look at a particular problem, a simpler toy model problem, just to kind of figure out as to under what circumstances would we be using the degenerate perturbation theory versus non-degenerate perturbation theory. Okay, so let us consider a simple two-state system. Okay, and if you are looking at two-state system, there is a part of the Hamiltonian which is exactly soluble, which has 2 energy levels, E1 and E2, and then there is another part of the Hamiltonian which you want to treat as a perturbation, say, and that is of course not diagonal. Okay, and you want to understand whether you want to treat this problem as a degenerate perturbation theory problem, or whether you want to treat that as a non-degenerate perturbation theory problem. Okay, So now remember that, like, I have written delta H to be delta H11, delta H22, and delta H12 at both ends. Okay, that is just for simplicity. I could have written down delta H12 star on this, which is the most general expression to write down, because delta H is Hermitian and a star put on that will ensure this thing. All I'm doing is assuming that delta H12 is real. Okay, that assumption may not be correct. If you want, you can put a star on this thing just to be on safer side. Okay.
Would you go back a few slides?
Yes, sure. Few slides.
Yeah, the multiple expansion part. After that.
Just a second. Here.
Yeah. Okay. I was just confused with the expression for a moment.
Oh, okay. So this is fine.
In the monopole term, we had some mu, like 1 by MP dependence, right?
No, not in the monopole term.
I mean, the 1 by MP dependence comes from the mu factor, I'm saying.
Yeah, but the mu factor sits in the dipole, no? Not in the monopole. This is the electric expansion, no?
Yeah.
Right. Magnetic monopole expansion doesn't exist. It starts with the dipolar quantity and comes with a mu, which
Yeah.
is 1 over MP. Okay.
I'm not talking about magnetic thing. I'm just saying what we computed earlier. We had 1 by something like m square by MP.
Yes, that was the dipolar contribution. This quantity. See, this is a dipolar term. This is magnetic dipole moment.
Yeah. Okay.
Yeah, so those factors are mass suppressed, even for the electronic case. Electronic dipole contribution, I mean, would be mass suppressed compared to the leading contribution.
All right.
Okay, so here we are. So, so the total Hamiltonian, of course, would take the form like this. Okay, E1 plus delta H11, E2 plus delta H22 diagonally, and delta H12 off diagonally. Okay. It's a 2 by 2 matrix. You can try diagonalizing it. Okay. So all you have to do is to kind of solve that secular equation, and this is the equation that you would get: lambda minus the first diagonal value times lambda minus the second diagonal value is equal to product of off diagonal terms. Okay. Quadratic equation, we can solve it. Okay. So here's the answer. Okay. So this answer, I forgot to write plus minus here. Okay. Yeah. Okay. Coming back to this. So so this is these are the two eigenvalues. The plus minus would appear soon there. Okay. And this is a expression for it. And we want to ask a question that under what circumstances would we be able to get some picture of what these eigenvalues are. Okay. And there are two possible scenarios. One is that when E1 minus E2 is large compared to delta H's, which are appearing inside the square root. And another scenario is the one where E1 minus E2 is small compared to the delta H's appearing in the expression. Okay, and we'll look at both of them. Okay. So let's start with the situation where E1 minus E2 is much larger than the delta H. Okay. If that is the case, then what you could do is that you can just pull E1 minus E2 out of this square root. Okay. And you can kind of treat delta H as small and do expansion. Okay. So what we'll do actually is we just pull out E1 minus E2 times delta H1 1 minus delta H2 2 whole thing outside, right? This is 1 plus 4 upon this quantity divided by this entire stuff. Okay, and expand that piece. When we expand, we really keep the first term. Okay, the term involving these fellows are not even looked at right now. Okay, so the leading order in perturbation theory, this is how it is going to look like. Okay, so now you can see that because of the plus minus sign, you get two eigenvalues. One eigenvalue is lambda 1, which is E1 plus delta H11. Okay, E2 and when you take the plus sign, E2 and delta H2 to cancel out. But if you take a minus sign, then the opposite sector cancels out and you get eigenvalue E2 plus delta H22. Okay. So if you do that, then you can clearly see that to leading order in perturbation theory, you have a correction to the eigenstate with energy E1 and to the eigenstate with energy E2 independently. Okay. This is what we would call non-degenerate perturbation theory. Okay, because you are not trying to solve a 2 by 2 matrix problem really, but you are solving a problem individually. This is the eigenvalue in state 1, and this is the expectation value of H in the state 1. Similarly, this is the eigenvalue for the state 2, and this is the expectation value of the perturbation in state 2. Okay, leading order term in Rayleigh-Schrodinger perturbation theory is just a diagonal element. Okay, for the non-degenerate problems. Okay. If the problem had been degenerate, then you would have to also consider H12 and H21 pieces, which of course don't seem to occur here if E1 minus E2 is large. Okay. What if the situation was exactly opposite? Okay. If the situation is opposite, then what you get is that you can treat E1 minus E2 as a small quantity, and in the square root, you can just get rid of that term first, okay, and write down this remaining expression in this particular fashion, okay. If you write down this expression in this form, then you clearly see that not just that the diagonal matrix element, but even the off-diagonal matrix element is important, and you need to kind of take that into account, okay. This kind of diagonalization problem is exactly like diagonalizing a 2 by 2 matrix element, okay. 2 by 2 matrix, okay, and therefore this is like a problem involving degenerate perturbation theory, okay. Now, after having kind of done this manipulation, you can actually appeal to physics and figure out as to why it is like this, okay. And the answer is simple, that if the initial energy splitting was large, which is like E1 minus E2 is very large, okay, and if the perturbation effect is small compared to the energy splitting, then of course the problem was non-degenerate perturbation theory problem. Okay, it is just that a priori you wouldn't know that what is the difference between E1 and E2, which you would say is large, and study a non-degenerate perturbation theory problem. Okay, so one has to kind of get an estimate of the order of magnitude correction that a perturbation would generate before embarking on this on whether to use degenerate or non-degenerate perturbation theory. Okay. Now, conversely, if the correction due to the perturbation is large compared to E1 minus E2, then obviously you would want to use the degenerate perturbation theory. Okay, and in that case of we will be kind of reduced, not reduced, but we will be kind of going back to the matrix problem. Okay, now this is of course a toy model where we just considered E1 and E2 as two states of a two-state quantum mechanics problem, and some hypothetical Hamiltonian delta H, which had both diagonal and off-diagonal entries, and we basically just gave order of magnitude arguments to decide whether to use degenerate or non-degenerate perturbation theory. Okay. If you want to utilize this in atomic physics, then you can clearly see that if you think of E1 and E2 as electronic energy states, okay, then there is really nothing to think about, because if you think of these as electronic energy states, then electronic energy states are separated by very high energy difference compared to, say, fine structure or hyperfine structure splittings. Okay, and therefore, if E1 minus E2 are differences in electronic energies, then you would always be using non-degenerate perturbation theory and never use expressions of this kind. You'd use expressions of that kind. Okay, but instead of doing that, suppose you are looking at problems where energy level splitting is small, like a fine structure splitting is what you are looking at, and you want to ask how does the perturbation delta H is affecting the fine structure splitting. Okay, then you may have to actually weigh the contribution of the perturbation vis-a-vis the energy splitting within the fine structure problem. Okay, so is there any question about this? Okay, so if not, then we could probably try setting up the Zeeman effect problem, although we will not solve the whole thing today, but at least get a picture as to what we are going to do. Sorry, scrolling a bit slow. Yeah, fine. Okay. Fine. So what we'll do is we'll consider go back to atomic physics problem and consider atom in a uniform magnetic field. Okay. Now, if you're looking at a problem like this, then we know what is the Hamiltonian. Okay. If you go back to the relativistic quantum mechanics problem, then we had seen this term appear naturally from the Dirac equation, where the magnetic field couples not to L plus S, but L plus 2S. And that is this gyromagnetic ratio effect of kind of getting a factor of 2 in front of this. Okay. Now, we want to study this problem. Okay. Typically, what one does is that since magnetic field is a vector, you can kind of choose a particular direction for that magnetic field. So, and instead of trying to do this in an isotropic way, you do it in a kind of axial way. Okay. And by that I mean that you choose magnetic field in a particular direction, and Z is one of the favorite ones to have. And if you do that, then L plus 2S quantity just reduces to LZ plus 2 times SZ. Okay, and this is kind of relatively simple problem to deal with. Okay, in reality, of course, both of them are essentially same. Okay, what we want to do is to distinguish this problem into two possible cases. One possibility is to have weak magnetic field, and the other possibility is, of course, to have strong magnetic field. Okay, so let us start with the weak magnetic field problem first. Okay, so if you have a weak magnetic field, that means B is small, then this would correspond to kind of case where you want to compare the splitting generated by this external magnetic field with the splitting that you have in the fine structure problem. Okay, and if the splitting is small compared to the fine structure problem, okay, then we would treat this as a non-degenerate perturbation theory. Okay, fine. Now remember, if you are trying to compare this with the electronic levels, which are like very high, okay, like even in hydrogen atom, the ground state energy is minus 13.6. Okay, And the first excited state energy is minus 13.6 by 4, right? Because energy levels are falling off as 1 over n squared. Okay, so 13.6 by 4 is a number which is like close to kind of 3, right? 3.1 or 3.2 or something like that. Okay, or maybe 3.4 or something. Okay, so so the point that I'm trying to get at is that energy difference between the ground state and the first excited state is quite a lot. 13.6 versus 3.4. Okay, so if you are looking at very small magnetic field, you will always use non-degenerate perturbation theory with respect to unperturbed Hamiltonian. But if you look at fine structure splitting, then those splittings are much smaller. And within those splitting, if you want to ask how you want to solve this problem, okay, even there, a small magnetic field would warrant only a non-degenerate perturbation theory. Okay, fine. Now, the fine structure problem is in fact solved by using a basis like this. Okay, NLS is equal to half JMJ basis. Okay, and the J values that are possible in this basis are J equals half, 3 half, dot dot dot, all the way up to n minus half. Okay, it goes up to n minus half because for a given principal quantum number n, L can take values only up to n minus 1. Okay, for example, the n is equal to 1, which is the ground state of the hydrogen atom, has L is equal to 0 only, and n equals 2 has L is equal to 0 and L is equal to 1 only. Okay, so highest value L can take is only n minus 1. Okay, so J can go only up to n minus half. Of these, like suppose you look at J equals half state, then J equals half state can come from vector addition of L is equal to 0 and S is equal to half, or L is equal to 1 and S is equal to half. Okay, both of them contribute to J equals half. Similarly, it is true for J equals 3 half, 5 half, and so on, that every value of J is contributed by two neighboring values of L. And this is something we had talked about earlier also, that a given value of J, you have two states of opposite parity. Okay, except of course the value J is equal to n minus half, which comes only from L is equal to n minus 1. The other state which should have contributed would have been L is equal to n. It doesn't exist if the principal quantum number is n. Okay, fine. So that is the kind of 2 times 2j plus 1 versus 2j plus 1 kind of degeneracy that these states would have had. Okay. Fine. So this is going to be kind of my last transparency today. So what you would do is that you can compute Jz on this state. This state is kind of state in which the fine structure problem is diagonal, but this basis is good basis for computing Jz. Okay, so that is what I said. That maybe not. Yeah. Okay, so Jz of course continues to be diagonal in this basis, and you just get some eigenvalue. But our delta H is not just Jz, it is Jz plus Sz, because L plus 2s will give you J plus S. Okay, and in case of magnetic field in Z direction, you get J plus Sz. Okay, so although Jz part of the perturbation Hamiltonian is diagonal in this basis, it appears that Sz is not, because Sz is not a good quantum number out here. Okay, so what we will do is we will switch the basis and compute the Sz matrix element in the basis in which Sz is diagonal. Okay, so that is done by sandwiching Sz between these states, and then you, between these terms, you insert ML-MS kind of states. Okay, and if you do that, then you can compute the SZ eigenvalue within the ML-MS basis. Okay, so I don't have that equation written down here because I think I had typed it, but it had some tech error, and because of which I had to kind of erase that, otherwise the file itself wouldn't compile. Okay, but let me kind of tell you what one does. That between SZ and the brass state, you introduce complete set of ML-MS basis states, and between SZ and the ket, you again introduce complete set of ML-MS basis states. Okay, then the matrix element of ML-MS of SZ within ML-MS states is simple. You can compute that. Okay, overlap of ML-MS state with this state is just the Clebsch-Gordon coefficient. Okay, so you get 2 Clebsch-Gordon coefficients times the matrix element of SZ. Okay, so therefore you should be able to compute this matrix element by just making a change of basis. Okay, fine. Once you compute this matrix element, you can put it back in. Okay, this fellow is anyway diagonal. This matrix element can be computed by changing basis. After completing the computation, you can kind of get terms which involves Clebsch-Gordon coefficient times the eigenvalue of SZ, and you can take that and put it back into the expression for delta H. Okay, and try to solve the problem. Okay, of course, what we will do is not do this, but we'll use a different technique for manipulating this expression, and that technique actually rests on the following fact, that the operator JZ and the operator SZ actually commute with each other. Okay, and because they commute with each other, you can write down the expectation value of SZ in the same basis. Okay, in other words, because JZ and SZ commute, okay, and SZ also would commute with L squared, okay, it is not going to change the value of the SZ is not going to change value of L, it's not going to change value of J, and it's not going to change value of MJ also. Okay, so you might as well be able to kind of compute the value of SZ in this basis. Okay, so what we'll do next time is precisely employ that technique to compute, instead of kind of going back and forth between ML-MS basis and carry the Clebsch-Gordon coefficients along with it. Okay, so yes, I may have just a line written out here. I had an expression, but like, it had some problem. So I think I'll stop at this point, and we can kind of take over this computation. We will do a few steps in the ML-MS basis, and then we'll take it up as to how to deal with this problem even without changing the basis. Okay. Any questions?
Hello, sir.
Yes.
Good morning, sir. Please keep these notes in Dropbox, because
yes, I have been keeping the notes in the Dropbox. Oh, sorry.
Because I want to read the nuclear